First of all, I'd like to thank deeply the organizers of this GIFT workshop this year. First of all, to choose this topic about the Mediterranean area, which is a very dear topic to me and to many others. And also for inviting me, of course. A good opportunity to share what we know, what we do with teachers, which is a very important matter to me. And so what I would like to do is to introduce somehow the geological evolution of the Mediterranean Sea region, not the sea itself, but the Mediterranean region. And after my talk, there will be the talk of Claudio Facchenna, who will see the same area from below, from the deep mantle, and he will be looking for the forces that drive and have been driven since the Cretaceous and are still driving today the tectonic evolution of the Mediterranean Sea. Okay, so our talks are complementary. I hope there is not too much of an overlap between the two, but I think it will be all right. Okay, so the Mediterranean Sea is a fantastic area. It's a fantastic natural laboratory. And for us geologists, geophysicists, geodynamicists, because it is in a rather small domain. It's much smaller than the Pacific, of course, but in a rather small domain, we have all the ingredients of plate tectonics, continental deformation, and we have a density of information that has been acquired since more than 150 years. First, the geologists working in the Alps, and nowadays the geophysicists working all over the world, and especially in the Mediterranean area. We have a density of information, geological information, geophysical information, including seismology, as Claudia will show you later this morning. We have a density of information that is equal to nowhere. There is no other area in the world where the density of information is so great. Maybe California, but I'm not even sure. So we have a fantastic playground here for us geologists. Okay. So let's start with the geodynamic and geological context of this rather small region, but for now it will be our largest playground. So I will use this map here, which is the geodynamic map of the Mediterranean that was published several years ago, and which is quite useful. So all the red lines you see here are the faults, active or recently active ones. Okay. So let's first look at the main ones. So you see here the thrust front of the Alps and the Carpathian here. We are standing somewhere around here now. The thrust front of the Pyrenees here, of the Betic Cordillera, the Rif, and all the Maghrebian chains here, the Atlas. You have, of course, here the front of the Zagros, the Caucasus here. We have the main subduction zones here. We'll come back to this later, of course. And we also have the Apennines here. We also have this big fault, which is very important in the dynamics of the area, which is the North Anatolian Fault. Okay. Now I've added here in this deep blue color areas where we have oceanic crust. Okay. But oceanic crust, which is rather old, okay, which is a Mesozoic oceanic crust. So you find, of course, the Mesozoic oceanic crust in the Atlantic here, mostly Cretaceous around here. But we also have old oceanic crust in the eastern Mediterranean here, where the African plate is subducting below, roughly speaking, Greece and Turkey. Okay? The age of this oceanic crust here is not precisely known. Okay? And the ages, they vary from the Carboniferous. A recent paper proposed that it is Carboniferous, which I don't believe, but it was published recently. And it can be as young as the late Cretaceous. Okay? I favor a late Jurassic age, but this is rather unknown. Okay? And then we have old oceanic crust, Mesozoic oceanic crust, probably Cretaceous, in the Black Sea here and in the southern part of the Caspian Sea. Okay? Then we have younger oceanic crust. We have young oceanic crust here in these basins that will be mentioned later on as back arc basins. This big one here, which is called the Liguro-Provençal Basin here, and the Algero-Provençal Basin in the south here. And within the Tyrrhenian Sea here, we have two domains where we have oceanic or quasi-oceanic crust here in the southern part of the oceanic crust. These three basins here are young. They are at most early Miocene in age, around 23, 24 MA for the oldest oceanic crust around here. And this one is very young, younger than 2 million years. Then we have all around these domains, we have young mountain belts formed since, say, 30, 35 million years. So we have, of course, the Alps here, we have the Apennines, we have the Gibraltar Arc here with the Betics and the Rif, the part of the Atlas here, of course, the Dagros, the Dinarids here. You see that the Carpathians have not been so much active during the Neogene here. And we also have here the subduction zones with the big accretionary wedges, which are now below the sea level, the Mediterranean ridge here, and the Calabrian accretionary prism here. What you see on this picture is quite peculiar. You see that these oceanic basins here, they open while these mountain belts were active. Okay, so you had extensional tectonics here, rifting a part of Corsica and Sardinia away from southern France and Spain here, and also opening of the Tyrrhenian Sea on this side, while all around you were building mountain belts with compressional tectonics. Okay, and we have to explain this. Okay. At the same time, we had extension that didn't lead to oceanic crust formation here, but nevertheless we have rather intense finite extension here in the Aegean domain or in the Panionian Basin, or of course all around here in the Tyrrhenian Sea or the Alboran Sea here. Okay. So let's have a look to the main episodes of deformation and the main geodynamic episode we have in this area. So I recall you this probably Jurassic Ocean here, which is a remain of a branch of the Tethys Ocean, which we sometimes call the Mesogean Ocean here. And this Mesogean Ocean was closed approximately at the same time as the large Tethys Ocean, which is just seen today as remains known as ophiolites. You know about ophiolites? Okay. Remains of oceanic crusts now sitting on top of continental crust. And these ophiolites, you find them from the very famous Oman ophiolite nappe here, to scattered ophiolites in Iran here, to Turkey here, and also Greece and the Dinarids, and of course part of the internal Alps here. Okay? And this oceanic suture is between Eurasia here and a continental block that was detached from Africa somewhere in the Mesozoic. And this block, which is here, is called either Adria or Apulia. Okay? And it collided with Eurasia, started to collide with Eurasia sometime in the late Cretaceous. Okay? Then we have something which is very important, which happened exactly at the same time as these basins here were extending, is of course the opening of the Red Sea, Gulf of Aden, and the rotation of Arabia, the separation of Arabia from Africa. Okay? This should not be neglected, as Claudio will show you. This has something to do with the extension in the area here. Maybe not. I don't know. And then we have, of course, the back arc basins, which I will be talking about. And then we also have magmatism here. And magmatism, if I I could have added also magmatism on this side, but I wanted to emphasize that while you had intense magmatism here, you also had intense magmatism here, and this magmatism has migrated from south to north, from the late Eocene all the way to the Miocene here, during the rotation of Arabia. Okay. These are the main ingredients. Now let's have a look to the dynamic evolution, so some kinematic reconstruction. We are 170 million years ago here, and you see Africa here, India, you see Eurasia, of course, and this is the Apulia, famous age block here, which is being separated from Africa through this mid-ocean ridge here, and this is the alpine ridge that will make the alpine ophiolites here. And this is the main subduction zone here with volcanism on top of it here. Okay? So Africa is moving north, and in the early Cretaceous, sorry, this is still in French, but Africa is moving north, and while it is moving north, it is extending. And you have lots of rifts here, shown in green, here in that part of the geological evolution. It's extending also above the subduction zones here in the Caspian Sea and the Black Sea. Okay. Late Cretaceous, now it's in English. We have this very important event of the ophiolite abduction that starts about this time here. So the whole northern part of Africa and Apulia is under compression here, and oceanic crust is being abducted on top of the continental crust. Late Cretaceous still, that's the end of the abduction period here. The naps, ophiolite naps are emplaced here, but the ocean is not yet closed. Okay. And the whole domain is under compression here. Eocene, 45 million years ago, we are under collision here. We'll just very soon reach the collision here, but it's not yet closed here. 30 million years ago, here we are in collision here, and we have the beginning of extension here in the Red Sea, Gulf of Aden. We have, of course, the big volcanic province here of the Afar here. And you see that now the Mediterranean is a closed domain, landlocked domain. Okay. Miocene, 10 million years ago, it starts to look as it is now. We have opened the Liguro-Provençal basin here, not yet the Tyrrhenian Sea here. And of course, the Red Sea and Gulf of Aden are actively opening. And this is the present, okay? Let's have a closer look to the Mediterranean domain now. So we have Africa here, Arabia, Eurasia, and all this complex domain in between here, okay? So let's have a look to a few features. Crustal thickness first. Crustal thickness, you see that in most, so you see the Moho depths here between 10 and 60 kilometers. You see that most of the oceanic, of the Mediterranean domain is underlain by rather thin oceanic crust, sorry. But this is mainly due to the presence of oceanic crust, which, as you know, is never thicker than 10 kilometers or something. Okay. Then you have rather thick crust below the mountain belts, of course, here. And thin crust also in continental domain, like the Aegean Sea or the Pannonian Basin here. Okay. If now we have a look now to the lithospheric thickness. The lithosphere is rather thin in the Mediterranean area, everywhere. So except here, because here you have you see the subduction of the Hellenic slab here, but you see that it is very thin here under the eastern part of Turkey. It's thin here under the western part of the Mediterranean here. And then, if we have a look to the, well, this is another model which is more extreme in terms of the thin character of the lithosphere there. If we have a look to the lithospheric resistance now, okay, what you see is, in general, the lithosphere is weak in the Mediterranean area. Of course, it's stronger here where we have the Hellenic slab, but in general, it's in the weak part of the gradients of lithospheric resistance in general. Okay, only red, white, and yellow colors in that area. So it's an easily deforming domain. The kinematics now, well, you see the convergence between Africa here and Eurasia. This is Eurasia is fixed in this picture. You see the fast motion of Arabia, and you see the still faster motion of Anatolia here, and you see this rotation. We'll come back to this a little bit later. Okay. The main ingredients of geodynamic ingredient, of course, in that area is subduction. And if we have a look to this section here, from Africa to the Balkans here, through the Aegean Sea and Crete and so on, you see a simplified picture of the African slab here, crossing the upper-lower mantle transition here. And above it, we have the Aegean domain. We'll be talking a lot about later on. Okay. So subduction of the African lithosphere in the mantle. We have frontal compression and shortening here. That's the Mediterranean ridge, the accretionary prism. And in the back arc domain, depending upon time, we have nowadays we have mostly extension, but before 35 MA in that area, we had compression. And there was a mountain belt being formed here before 35 MA, which is known as the Hellenides. Okay? And after 35 MA, it started to collapse because the dynamics of subduction changed. So what about finite deformation? In that area, we have mountain belts being formed, and we have extensional basin, as I said already, okay, at the same time. And this is very important. We also have high pressure, low temperature metamorphism, blue schist and eclogite. Okay? And they are all over the place, from the Alps to the Betic Cordillera or to Turkey here. And these sign past subductions. So we can use them to reconstruct the evolution of subduction zones through times. Okay. So they were formed in the depth of subduction zones here, and now they are now at the surface. Okay. And we can study them, study their deformation, past kinematics, pressure, temperature evolution. And they are very precious to specialists of tectonics in that area. Okay. They are very characteristic because in a PT diagram here, these rocks, they were equilibrated along this sort of gradient, which you can compare to this sort of gradient, which is a sort of an equilibrated gradient, like the one we may have below our feet. And this one is high pressure, low temperature. It's colder, typical of what is expected in the deep parts of subduction zones. Okay. So these extensional basins, just once more, the Alboran Sea, the Liguro-Provençal Basin here, the Tyrrhenian Sea, the Aegean Sea, and there would be also the Pannonian Basin, but I will not be talking about the Pannonian Basin today. Back arc extension started, or rather accelerated, some 35 million years ago. Okay, so there's a big change in the Mediterranean area some 30, 35 million years ago. Let's have a look to a section. Sorry, I go too fast. Okay, let's have a look to a north-south section from Africa to the Balkans here. So you see this section at lithospheric scale. This is Africa. This is the Moesian platform here in the Balkans. You see the Aegean Sea here, underlain by a rather thin crust, 23, 25 kilometers only, still thinner in the Cretan Sea here. This is Crete, this is Santorini, the active volcano, and this is the subduction zone here. Okay? And this is the trace of the North Anatolian Fold. And you see the age of the high pressure metamorphism that is decreasing from the north to the south here. Okay? And the age of a younger episode of high temperature metamorphism that is also younger in the south than in the north. So everything in that area is migrating. The thrust in the Hellenides, laterally, and also the high pressure metamorphism. The volcanic arc is migrating, as you will see, through time. And this I'll be talking later on. Let's have a look, for instance, on this section. Here you have the age in million years. And here you have the latitude. So here in the north and here in the south. That's the present day's thrust front. Okay? And this black thing that will turn to red here is volcanism and plutonism, magmatism in general. And you see that from 80 million years all the way to 35 million years, the magmatism stayed at the same place, okay, in the northern part of the section. Okay. And afterward, after 35 MA, the magmatism moved rather quickly to its present position, okay, southward. Okay. Thrust fronts have migrated too. The high pressure metamorphism has migrated as well. Okay? So 35 MA is a big change here, where the volcanic arc, the magmatic arc, has suddenly started to migrate toward the south to reach its present position, where you can see it now with the Santorini volcano, for instance. Okay? So this state is very important. So we have here the compression between the relative motion of Africa with respect to Eurasia, and you see that we are in a compressional, convergent geodynamic context, convergence between Africa and Eurasia here. Still, after 35 MA, we had the opening of these basins, okay, in this convergent domain. So within the convergent geodynamic context, extensional basins have opened after 35 MA. So which forces control this evolution, and which dynamic relation between convergence, subduction, and extensions? But let's have a look to the active Mediterranean tectonics. Seismicity first. You see this is from a paper that Claudio was a leading author of. You see that seismicity is all over the place, of course, along the main subduction zones here. And of course, in the eastern part of the domain, it's very active here. Okay? Not very deep, usually. Then we have the focal mechanism of earthquakes that tells you which type of fault is active during an earthquake. These are reverse faults in red, normal faults, and strike-slip faults here. And you see that you have all types of faults in that area. Of course, strike-slip faults, earthquakes are concentrated along this main fault, the North Anatolian fault here. And reverse type faults are concentrated along the main subduction zone, which is the Hellenic subduction zone here. And you see that in many mountain belts, like the Apennines, what you have is mostly extension. Okay? And all the earthquakes that are very famous in that area, most of them are extensional earthquakes. So the Apennines, it is a mountain belt, but it is collapsing now. Okay? It's under extension. Okay. In that area, you have a mixture of compression, extension, and strike-slip faults here. And you see that the Alps are not very active anymore. Okay. And if I go back to this region here with compression in the south, strike-slip in the back, and extension here. Okay. Lots of extensional earthquakes here. And indeed, normal faults, extensional faults, are very frequent in the Mediterranean domain. Okay? And this normal fault in Crete here, the Lasteros normal fault here, is quite spectacular. But you can see many of them all around the Mediterranean, including the Apennines, where they are very active. Okay? GPS velocity field here, well, you see the slow motion of Africa with respect to Eurasia, and you see the very fast motion of Anatolia with respect to Eurasia, okay, along this big fault here, the North Anatolian fault. Okay, Carlo mentioned the future Istanbul earthquake, and of course it is along this big fault. Okay, the Marmara Sea earthquake. Okay, you see a little deformation here within what we may think is Eurasia. Here, the relative motion between the Apennines and the stable Eurasia. If you look at the same sort of velocity field, but with Africa fixed here, you see better the convergence between Africa and Eurasia, because there are more GPS stations in Eurasia than in Africa here. And still you see that it doesn't change very much the picture around here. Why? Because this motion is much, much faster than the convergence between Africa and Eurasia. Okay. So whatever the reference frame, you always see this rotation of Anatolia and the acceleration of the motion from here all the way to here. Okay? So what's very important is that in the Mediterranean we have something which is very characteristic. We have internal displacement which are faster than the motion of the two main plates at the boundary of the system. Okay. So what's the engine? Okay. Just a brief look to active and recent volcanoes, of course, and they are, you know all of them. Okay, and the most famous one of the most famous one is Santorini here, where you see the caldera here. Okay, and active centers north of the main caldera, especially here in the Colombo area. Okay, a few images just to give you the idea of visiting this place if you have not done it yet. Okay, so Santorini is a nice place for volcanology, for swimming, for anything you like. Okay. There is not only volcanology. You said food. Yes, food in Greece is fantastic. Geothermal resources. That's a very important indicator of geodynamics as well. You see here on this map here of geothermal resources in Europe that the southern part of Europe, and especially this area here and this area, are very hot in general. Okay, and the most active developing area, one of the most actively developing geothermal energy in the world is Western Turkey nowadays. Okay, so these are some of the recent geothermal plants in Western Turkey here. Okay, and what's very important is that here you have hot water, hot springs, okay? And the hottest water that are shown with this brown color here, okay? And you see that most of the hot springs, the hottest one, they are in the western part of Turkey, okay? Where you have almost no active volcano, okay? Most of the recent active volcanoes, they are in the eastern part of Turkey. And the recent you see here Pliocene Quaternary volcanic rocks here in white, and in gray here you have Miocene volcanic rocks. So it's an area where you have mostly a Miocene magmatism. Okay, there is one recent volcano which is the Kula volcano that's around here, but only one. Okay, most of the recent volcanoes they are in the east here. So we have active hot spring, and the hottest one in an area where we don't have active volcanism. Okay. And it's not magmatism itself that controls the position of these geothermal thermal fields, it's tectonics and geodynamics. It's because the mantle is very close to the surface and because it's very hot in that area that we have these geothermal fields there. Okay. So it's a very important indicator. And you see here on the map of the western part of Turkey, this is the Menderes Massif, the main faults here, main grabens, the Gediz graben here, or the Büyük Menderes graben here, or the Simav graben here. You see that the thermal plants or hot springs, the main ones, are all associated with the faults here. Okay, and here as well. So some pictures of these faults. You have an active normal fault in the Büyük Menderes graben here. This is the steep fault, normal fault. This is a rather steep fault also, the Simav graben in the north here. Two normal faults here and here on either side of the Gediz graben here, which is with very active geothermal energy recovery. And here, this is a normal fault. Okay, normal fault in that area is just like this, a very shallow dipping normal fault that has accommodated a lot of extension. Okay, you may think that usually normal faults are steep, but many normal faults are shallow dipping. Okay, they are called detachments here, and this is one of the most spectacular ones in the Mediterranean area. And this is another view of it. You have the metamorphic basement here, Miocene sediments, and just in between there is this shallow dipping fault. And when you walk around here, you walk on the fault plane. Okay, and these faults. The steep faults and the shallow dipping fault that conduct the cold water from the surface down to the middle crust, and also the reverse motion of the hot water from the depth of the system all the way to the surface. Okay, and the hot springs occur here. Okay, and this abnormal geothermal gradient that we have here is a result of subduction dynamics, slab retreat and slab tear. Let's focus on the Aegean region now. Seismicity, and you see here with the seismicity that you have compressional seismicity in that area, extensional, that's the blue ones in that area, and strike slip along the North Anatolian Fault here. You see a concentration of extensional features here, faults here, earthquakes here, which is the Corinth Rift. Okay. So compressional features, the Mediterranean Ridge, the Calabria Wedge here that signed the present-day subduction. Very thick features like here the Mediterranean Ridge, where sediments have accumulated since the Miocene above the subducting African oceanic lithosphere here. Let's have a new look to the GPS velocity field. You see the motion of Anatolia here, and you see that the vectors, they are longer here than here. Okay, that signs that, of course, is due to the extension you have here in Western Turkey and the Corinth Rift. And if we have a look to the same data set here, not with fixed Eurasia, but fixed Anatolia here, okay, so the reference point is here in Anatolia. There is no motion anymore in Anatolia because Anatolia moves rigidly. You see that Eurasia is moving fast toward the right, and you see that the southern part of the Aegean is moving rather fast toward the south. So, of course, between this and this, we have extension here, and extension here. Okay, extension in the Corinth Rift here, and extension in the western part of Turkey with the grabens I have just shown you around here, with lots of earthquakes, rather big extensional earthquakes. And the velocity of extension is 1.5 centimeters per year across the single Corinth Rift, which is a very fast continental extension. They're 3 times faster as the Baikal Rift, or 3 times faster as the East African Rift. Okay. And the western part of Turkey is also more distributed, the extension is more distributed, but the total extension is around 2 centimeters per year. Okay. So in this, sorry, this should be above, but an extensional component here, and this extensional component is not recent. It started some 30, 35 million years ago. And this whole domain here has been extending since 35 MA in a distributed fashion here. We'll come back to this later on. Okay, so extension in this domain here. So which are the forces that drive the deformation of Anatolia and the Aegean region? Is it the collision between Arabia and Eurasia, a sort of extrusion mechanism here? Or is it the retreat of the subduction zone here, slab retreat here, maybe a combination of the two, as we'll see afterward. And which is the cause of the localization of deformation some 5 million years ago with the creation of this big fault here, the North Anatolian Fault. Let's focus a little bit on the Corinth Rift. Let's go back to this north-south lithospheric section of the Aegean here, okay? And so this is here. So let's have a look to the evolution of that area here from the late Eocene, early Oligocene. So you see the situation. We have subduction of the oceanic lithosphere here, starting here. Very active here with the collision of Apulia here in the formation of mountain belts. Here the Hellenides, and here, of course, the end of the Pyrenees, but part of the Alps here, and here the future Betic Cordilleras. Okay, this is a hinge period here, where we move from compression in the back arc regions to extension. Okay, and this is 23 million years ago in the Aquitanian. Here you start to open this basin here. You start extension here. Okay, and progressively you see that slabs are retreating here. And progressively you open these basins, large oceanic basin here, And you see that we are now in the late Miocene. Early Messinian, of course, it's in this configuration that you will have the desiccation of the Mediterranean, and you will have a conference on this episode, which is a major thing here with the deposition of salt and gypsum all around and the Mediterranean and in the deep basins here. And after that, in the Pliocene, you have the opening of the southern part of the Tyrrhenian Sea here, and this is the present stage. Okay, so just to give you a more dynamic view, can move faster, and you see that the slabs here, the subduction zones, are retreating. Here it's retreating southward, here eastward, and here westward. Okay. Okay, and this is the displacement of the trenches here from 30 million years to the present, or here from 30 million years to the present. Okay, the displacement since 70 million years. This is the displacement of Africa with respect to Eurasia here, and you see that the displacement here is this long here in 70 million years, and this is only in 30 million years. Okay. So you see that this part of Italy here has moved with respect to France, for instance, about the same distance or a longer distance than Africa in 30 million years, and Africa has moved in 70 million years with respect to the same point. Okay, so even on the long term, the displacement of internal domains in the Mediterranean are much faster than the displacement at the boundary between Africa and Eurasia. Let's make a synthesis of the geodynamics of this area. You see, this is Africa here, and this is the Balkans here. This is the evolution of the same section I showed you. Okay, and you see the progressive closure of this oceanic domain here. You see the subduction of this block here, which is Apulia, the formation of a mountain belt, and then extension. Okay. So you see here the subduction of this block here. We make a mountain belt, and then from 35 MA it is extended. So we first make the subduction, by subduction of the continental domain, we make the mountain belt, and then the slab retreats, and the whole domain is extended. Okay, and during this episode we have the formation and exhumation of this blue material here, which is the blue schist and eclogites. We don't have time to show you. And this is the evolution here, Africa, Eurasia, and you see the formation of the mountain belt here, and then the slab starts to retreat, and you have the spreading of the mountain belt in the present day situation. Okay, this is another view, a numerical simulation by some colleagues here in Rennes and Paris, and you see exactly the same thing, but numerically simulated here, with the subduction of the African lithosphere here, again, okay. And you see that materials is subducted. If you look at the blue material, subducted and then exhumed, subducted and then exhumed for the green material. Okay, so you same story. One drawn by a field geologist and another one produced by numerical simulation here. Okay, another one which is not in the same area but is very similar to show you the exhumation of metamorphic rocks. You see them here getting down here, and at some stage the subduction regime changes because you'll have slab detachment here, and the material is coming back to the surface. Okay, and that's why you observe the eclogites and blue schist in the Mediterranean domain. Okay, so to finish up, you see here the same reconstructions here. From this reconstruction, you can calculate, you can measure the convergence here, which is about 800 kilometers, okay, between Africa and Eurasia. The slab retreat, since 65 million years, is about 700 kilometers. Since 30 million years, it's about 500 kilometers. Okay? But if we start with 65 MA, the total length of lithosphere that went down into the mantle is the sum, you have to add convergence here, plus slab retreat. Okay, and this makes 800 plus 700, which gives 1,500 kilometers. Okay, with of course an error bar, which is rather large, but it gives you a first order figure, 1,500 kilometers. And completely independently, you can compare this with the length of the slab you see in tomographic models, okay, which is also approximately 1,500 kilometers. Okay, so you see that from the geology, okay, this is purely the work of a geologist, and this is purely the work of a geophysicist. You come up with approximately the same figure. Okay, and so it's very likely that the complex evolution of the Eastern Mediterranean area has been driven through time by only one subduction, which is the subduction that we see today in the dipping here, hanging in the mantle. Okay, and then this slab is more complex. It's been torn in several pieces here, and I just would like to finish up with this. The shape of the slabs below the Mediterranean, you see that its shape is quite complex because of 35 million years of slab retreat. It's been deformed, it's been detached, it's been torn, and in some areas like below Turkey, you have no slab left here. Okay, and you see its complex shape. And this of course, has consequences on the deformation at the top in the crust. Okay, and I think I have to stop here. But Claudio will show you more about the effect of what is going on below the Mediterranean and its consequences on what we can see at the surface. Thank you.